Okay, guys, the second fundamental theorem of calculus. I apologize for not being there with you guys today. I've been feeling well all week. I went to the doctor this evening. I do have strep throat, so I think it's best that I stay home for at least one day. That way I'm not as contagious. Let me see if hopefully we can get through this. And remember, at the end of the period, the last 35 minutes or so, you're going to get to be able to pick a partner, use your notes. You're going to take that quiz. But before that, let's go through the second fundamental theorem of calculus. Alright, so we have seen that the definite integral of f on the interval a to b was defined using the constant b as the upper limit and so forth. Now, what we're going to see here is the second fundamental theorem of calculus is saying that we have the region from a to b. And then you have the function. If we go and we say from a constant to a variable, okay, so that's the key here. Constant to a variable. So I say, if I ask you to evaluate this from 0, when x is 0, when x is pi over 6. So what we would do is, we would simply take the derivative of cosine of t, or the antiderivative, excuse me, and the antiderivative of cosine of t is sine of t, from 0 to x. And then I can plug in any of these values and evaluate. So what we discover is, in this first one here, I have sine of x minus the sine of 0, yes, and we know the sine of 0 is 0, so I'm left with just sine of x. So you can see how the antiderivative from 0 to x cosine t dt is the area under the curve depending on where x lies. So what we're doing is we're accumulating the area, and then what we discover is this, and this is the second fundamental theorem right here. The derivative of the antiderivative from a constant to x, f of t d of t, is simply equal to f of x. Now, what I don't like about this is you replace this f of t with x. What you don't see is that also, I want you to understand that it's also the derivative of that upper bound. So also the derivative times, so we're going to add into this times the derivative of that upper bound. Now, this is your upper bound, x. Obviously, the derivative of x is 1. That's why they put just f of x. But I'm going to give you some examples where it doesn't, where it's going to make a little bit more sense. So, if I give you this one, we'll start off with the straightforward one. So this, notice how it says the derivative of the antiderivative from a constant to a variable boundary. What we do is we plug in x into t, so instead it becomes x. And what's the derivative of x1? So this is your answer, x. Okay? That one's easy, right? Now, if I wanted to show you the work behind it, we could, okay, that's your answer, but watch this. So we could, if you will, we could take the antiderivative of t, which is 1 over 2 t squared from x to 2. I could plug in my x, so 1/2 x squared minus, I could plug in my 2, so 2 squared is 4, half of 4 is 2, but then look, there's a derivative out in front. And what's the derivative of 1/2 x squared? X, what's the derivative of negative 2? Gone. So there's my answer, x. So let's just take that and apply it. So, if I have the derivative of the antiderivative from a constant to a variable, 2x of t squared, what you do is you plug in 2x right here for t. So we know, we know this one right here, right? We know that 2x, doggone it, 2x squared, but then also you need to take the derivative of 2x, which is 2. So it's 2 times 4x squared, which gives me 8x squared. Okay? So what I'm going to do is I have the derivative from a constant to a function. I'm going to plug in x squared for t. So 3x squared squared, because t is squared is x squared. And then I'm going to multiply that by the derivative of x squared, which is 2x. So it gives me 3x to the 4th times 2x, which gives me 6x to the 5th. Okay. Now, notice on this one, I have from a variable to a variable. Now, this we got to do, because it's always, every time it's been from a constant to a variable. Between x and 2x, what we're going to do is, we know there's some value, some constant between x and 2x. So what I'm going to do is I'm going to put the derivative, d of x, times, I'm going to go from x to some constant c that's between 2x, so x to c of t plus 1 quantity squared d of t, plus from c to 2x. Notice again, I said there's something between x and 2x. I'm calling it c. So from x to c of t plus 1 quantity squared d of t, and also c to 2x of t plus 1 quantity squared d of t. Now, what we can do now is, now it's always been from a constant to a function. So why don't I just say, couldn't I just flip that and say from c to x if I put a negative out in front? So what I'm going to do is I'm going to say negative. I'm going to plug in this x that's up here now into here, so it becomes x plus 1 quantity squared. And the derivative of x is 1, plus, I'm going to plug in the 2x plus 1 quantity squared times the derivative of 2x, which is 2. And guys, you're fine leaving your answer just like that. Again, this negative is coming from this property where c to x would be the negative, and then I can do the fundamental theorem, plug that in, and then derivative of 1 is 1, or of x is 1. Okay? So you've already been assigned the 4.4 WebAssign. What I want to do is I want to add to that. I want you guys to do page 328, 5 through 23 odd. Those are the first fundamental theorems of calculus, which was all your WebAssign. And now let's add in some 87 through 96. This is the second fundamental theorem of calculus right here. So I want you to do 5 through 23 odd, 87 through 96. You guys can work on that. The sub, I don't even know who our sub is going to get you ready to go. You can pick a partner. If there's an odd group of 3, those are the only 3 that can work together. If not, it's partner of 1 only. And hopefully I'm back on Friday, Thursday, Friday. Thanks.